Hello friends, welcome you all to the 31st lecture on functional analysis and its applications. In this lecture, we will discuss the application of polarization identity. This is the content of today's lecture, that is application of polarization identity. Theorem: if B is Banach space whose norm obeys the parallelogram law and an inner product obeys polarization identity respectively as equation 1 and 2. Then B is a Banach space. Equation 1 is known as parallelogram law. Square of the norm of x plus y plus square of the norm of x minus y equal to 2 into square of the norm x plus square of the norm y. And polarization identity 4 into inner product of xy equal to square of the norm of x plus y minus square of the norm x minus y plus I square of the norm x plus iy minus I into square of the norm x minus iy, where I is the iota. I is equal to under root minus 1. Proof: since B is Banach space, then B will be Hilbert space if inner product defined in equation 2, that is polarization identity, satisfies all the following conditions of her inner product. First, inner product of xx greater or equal to 0 and inner product of xx is equal to 0 if and only if x is equal to 0. Second, conjugate complex of the inner product of xy equal to inner product of yx. Third, inner product of x plus y z equal to inner product of xz plus inner product of yz. And fourth, inner product of alpha xy equal to alpha into inner product of xy for all x, y, z belonging to B and alpha B scalar. We shall prove them one by one. Let us prove one by one. That is first, replacing y by x in equation 2. Equation 2, that is polarization identity. That is 4 into inner product of xx equal to norm x plus x square, because here we replace y by x, that is this minus norm of x minus x square plus I norm x plus I x square minus I norm x minus I x square. Okay, so x plus x, that is 2x, so equal to norm 2x square, this is norm 0 square, and here x common, that is I into norm 1 plus I x square minus I into here also x common, so I into norm 1 minus I x square. Okay, so norm 0, that is 0, and this is 4 norm x square, because we know that norm of alpha x is equal to mod alpha norm x. Okay, so here square and alpha is 2, that is 4 norm x square plus I, and this is 1 plus I, that is scalar alpha, so mod 1 plus I square into norm x square minus mod 1 minus I square into norm x square, because here alpha is 1 minus I, equal to 4 norm x square, and we know that z is equal to x plus iy, that is mod z is equal to under root x square plus y square. Okay, so here x is 1 and I into 1, y is 1. Okay, so under root 1 plus 1 under root 2, and this is square term, that is 2. Okay, so 4x square plus 2 I, and value of this is under root 2 square. Okay, that is 2. So this 2I into norm x square. Similarly, this also minus 2I norm x square. Okay, so this one and this one cancelled out. This is negative and it's positive. We have 4 norm x square. So here 4 into inner product of xx is equal to 4 inner product of x square. This implies that inner product of xx is equal to norm x square. This shows that inner product of xx is non-negative, and inner product of xx is equal to 0. This implies that x is equal to 0, because inner product of xx is equal to 0. This implies that norm x square is equal to 0. Norm x square is equal to 0, that is norm x is equal to 0, and we know that if norm x is equal to 0, if and only if x is equal to 0. Hence, condition first is satisfied. Second, to establish second, we shall take conjugate complex of both sides of equation 2. So we have this one, and equation 2 is this. So taking the conjugate complex of both sides of equation 2, we have 4 into conjugate complex of the inner product of xy is equal to this one, and this is the whole conjugate complex of this expression. Okay, so this is real, and this part is complex, and this is also complex. Okay, we know that conjugate complex of z1 plus z2 is equal to z1 bar plus z2 bar. Okay, so we can write the conjugate complex of each term. Okay, so this is real part, so norm of x plus y square, and this is minus norm of x minus y square, and here conjugate complex. Okay, so conjugate complex of I is minus I. So this term can be written as minus I norm x plus iy square. Similarly, this plus I norm x minus iy square. Okay, so this can be written as norm of y plus x square minus, here common minus 1, that is we can write minus 1 into y minus x square. Here we can write by taking I common. So minus I, and this I common, y minus ix. Okay, so I into norm y minus ix square plus I minus I common here. Okay, so norm minus I into y plus ix. Okay, again apply the property norm alpha x equal to mod alpha norm x. Okay, so this is as it is, and this one minus 1 as alpha. So mod minus 1 square into norm y minus x square minus I into mod I square into norm y minus ix square plus I mod minus I square into norm y plus ix square equal to norm of y plus x square minus norm of y minus x square minus I mod I square, that is 1, norm y minus ix square. Similarly, this is also plus I norm y plus ix square. Okay. So this expression can be written as, this is here and this is here. So norm y plus x square minus norm y minus x square plus I into norm y plus ix square minus I norm y minus ix square. As per the definition of polarization identity, we can write this is 4 into inner product of yx. So 4 and 4 cancelled out. So we have conjugate complex of the inner product of xy equal to inner product of yx. Second, established. Third, replacing x by x plus y and y by z in equation 2, that is 4 into inner product of x plus y z equal to square of the norm x plus y plus z minus square of the norm x plus y minus z plus I into square of the norm x plus y plus iz minus I into square of the norm x plus y minus iz. Now, square of the norm x plus y plus z can be written as norm of the square of x plus z plus y. So there is no change. We can write this. Replacing x by x plus z in equation 1, we get square of the norm x plus z plus y plus square of the norm x plus z minus y equal to 2 into square of the norm x plus z plus 2 into square of the norm y. This implies that this is in right side. Okay, so we can write this expression and denoted by equation 4. Equation 4 rewritten as the square of the norm z minus y plus x square. Okay, here first term this, so here 2 into norm of x plus z square. Okay, so in this here first z minus y. Okay, so right side 2 into norm of z minus y square. Okay, we can write, and second term here 2 into norm of y square. Okay, and here second term x. So we can write second term of right hand side of 4. This is 2 into norm of x square and minus here norm of x plus z minus y square. Okay, so here we can write this is z minus y minus x. Okay, this can be written as minus norm of z minus y minus x square. This is equation 5. This can be written as per 4. We can write Okay. Now, norm x plus z minus y square equal to norm z minus y plus x square. Correct? No change? Equation 6. Using equation 5 in 6. Okay. So, here value of square of the norm z minus y plus x is this. Okay. So, from 5 and 6 we have norm of x plus z minus y square equal to 2 norm of z minus y square plus 2 norm of x square minus square of the norm z minus y minus x. Now, this can be written as 2 minus 1 common here. So, we can write this plus 2 norm x square minus again common minus 1. So, this can be written as x plus y minus z. Okay. So, this can be rewritten as this. Again, apply the property norm alpha x is equal to mod alpha norm x. So, this is mod of minus 1 square, that is 1. This is also mod of minus 1 square. So, this expression can be written as 2 norm y minus z square plus 2 norm x square minus norm x plus y minus z square. Equation 7. Using equation 4 and 7. Okay, what is 4? This one and 7. This. So, norm x plus z plus y square equal to 2 norm x plus z square plus 2 norm y square and putting the value of square of the norm x plus z minus y from 7. Okay. So, we get this one. Okay. And this can be rewritten as norm of x plus y plus z square minus, here this is minus minus plus and this is in left side. So, minus norm x plus y minus z square equal to 2 norm x plus z square plus 2 norm y square minus 2 norm y minus z square and this is minus 2 norm x square. This is equation 8. Interchange x and y in equation 8. So, this is x plus y plus z. If you change the x and y in this term, no change. That is, we can write norm of x plus y plus z square minus norm x plus y minus z square. Okay. Here 2 norm y plus z square. Okay. Because we change x and y. And this is 2 norm x square and minus norm x minus z square minus 2 norm y square. This is equation 9. Adding equation 8 and 9. Okay. So, we have 2 into this equal to 2, 2, 2 and 2 also here. Okay. So, taking the common of both sides 2 and cancel out. So, we have after addition of equation 8 and 9 we get equation 10, that is norm x plus y plus z square minus norm x plus y minus z square equal to norm of x plus z square minus norm x minus z square plus norm y plus z square minus norm y minus z square. Now replacing z by iz in equation 10 and multiplying both sides by I. Okay, so replacing z by iz. Okay, here also, and multiplying both sides I. This is equation 11. By adding 10 and 11 we get 10 is this and 11 this. So we have this expression. Okay, norm of x plus y plus z square minus norm x plus y minus z square plus I norm x plus y plus iz square minus I norm x plus y minus iz square equal to norm x plus z square minus norm x minus z square plus I norm x plus iz square in this. Okay, so we can write this again. This term after addition we can write here. So in one bracket this, and in second bracket norm of y plus z square minus norm y minus z square plus I norm y plus iz square minus I norm y minus iz square. Okay, so this one and this in second term. So as per the application of polarization identity, we can write this 4 into inner product of x plus y z equal to 4 into inner product of x z plus 4 into inner product of y z, this one. So 4 common and cancel out. So this implies that inner product of x plus y z equal to inner product of x z plus inner product of y z. Okay, so third condition also satisfied. Now we shall establish the result inner product of alpha x y equal to alpha into inner product of x y in several steps according as the scalar alpha takes the different type of values. That is, alpha is positive integer, alpha is negative integer, alpha is rational number, alpha is real number, and alpha is complex number. Okay, so we prove it for each scalar one by one. Okay, suppose alpha is positive integer in inner product of alpha xy. As proved in third, we have inner product of x plus zy equal to inner product of xy plus inner product of zy. Replacing z by x. So this expression can be written as inner product of x plus xy equal to inner product of xy plus inner product of xy. Okay, so here inner product of 2xy equal to 2 into inner product of xy. So this result is true for alpha is equal to 2. Okay. Now assume that fourth condition is true for any positive integer n, that is inner product of nx y equal to n into inner product of xy. Then inner product of n plus 1 into x y equal to inner product of nx plus x y. Okay, so by third property of inner product, this can be written as inner product of nx y plus inner product of xy. So this can be written as n into inner product of xy by this property and this as it is. So inner product of xy common, so this is n plus 1 into inner product of xy. So it is true for n plus 1 also. So this condition is true for positive integer. Second, B part, if alpha is negative integer, first we shall prove that inner product of minus x y equal to minus into inner product of xy. Replacing x by minus x in polarization identity given in equation 2. 4 into inner product of minus xy equal to norm minus x plus y square minus norm minus x minus y square plus I norm minus x plus iy square minus I norm minus x minus iy square. This implies that 4 into inner product of minus xy equal to this one, taking minus 1 common in each term. Okay. So above expression can be written as this by common minus 1. Again, applying the property norm alpha x is equal to mod alpha norm x here. Okay. So we get this norm x minus y square minus norm x plus y square plus I norm x minus iy square minus I norm x plus iy square. Now taking minus 1 common. So we can write this is as this one and this is here and this is here and this. Okay. After taking the minus 1 common. So this can be written as minus 1 into 4 into inner product of xy. So 4 and 4 cancel out. So we have inner product of minus xy equal to minus inner product of xy. Okay. Now let alpha is equal to minus beta where beta is positive integer. Okay. Now inner product of alpha xy equal to inner product of minus beta xy. As per this, we can write minus inner product of beta xy. Okay. So beta is positive integer. So by first property, if alpha is positive integer. So here beta is positive integer. So this can be written as beta outside. That is minus beta into inner product of xy. Minus beta is alpha. So that is alpha into inner product of xy. So here we proved inner product of alpha xy equal to alpha into inner product of xy. Hence, condition 4 is true for all negative integer alpha. See, if alpha is rational number, let alpha is equal to p by q, where p and q are integers with q not equal to 0. We have inner product of alpha xy equal to inner product of p by q xy. Okay, alpha is equal to p by q, rational number. Let x by q is equal to z. So this can be written as inner product of alpha xy is equal to pz y. Since p is an integer, then using above a and b, if p is positive and negative integer, so we can write p outside, that is p into inner product of zy. Equation 12. Also inner product of zy can be written as 1 upon q into inner product of qzy. because q is integer. So as per B and A condition, q can be written as outside the inner product, that is q by q cancelled out, so there is no change. So inner product of zy can be written as this, equation 13. From 12 and 13, inner product of alpha xy is equal to p into inner product of zy equal to p by q into inner product of qzy, okay, by equation 30. This implies that alpha is p by q. So inner product of p by q xy equal to p by q into inner product of qzy. Qz is x. So this can be written as p by q into inner product of xy. Hence equation 4 is true for all rational number alpha also. If alpha is real number, let alpha be any real number, then there exists a sequence alpha n of rational number such that alpha n tend to alpha as n tend to infinity. Okay. So this is the general. If any sequence alpha n of rational number, then alpha n converges to alpha, where alpha is real number. Okay. So rational number converges to real number as n tend to infinity. For example, we can see that suppose alpha n is equal to 1 plus 1 by n power n, which is a rational number, where n is natural number. So this is a rational number. So limit n tend to infinity of this, that is e, which is a real number. Okay. So as n tend to infinity, rational number tend to real number. So by inner product alpha n into inner product of xy, where alpha n is rational number. Okay, so as n tend to infinity, it tend to alpha into inner product of xy as n tend to infinity, and also inner product of alpha n xy tend to inner product of alpha xy as n tend to infinity. Okay, and norm alpha n x plus y tend to norm alpha x plus y. Okay, as n tend to infinity. So using two polarization identity for rational number sequence, here alpha n of rational number. So using polarization identity for the sequence of rational number as this, 4 alpha n into inner product of xy is equal to 4 into inner product of alpha n xy. Okay, so we can write because alpha n is rational number. So as for polarization identity, we can write this expression. Okay, square of the norm alpha n x plus y minus norm alpha nx minus y square plus norm alpha nx plus iy square minus norm alpha nx minus iy square. Okay, taking limit n tend to infinity. Limit n tend to infinity, alpha n tend to alpha, okay, as n tend to infinity. So this is 4 alpha into inner product of xy, and this one as this can be written as norm of alpha x plus y square. Similarly, second term can be written as norm alpha x minus y square plus I norm alpha x plus iy square minus I norm alpha x minus iy square. What is this? This is 4 into inner product of alpha xy. So 4 and 4 cancelled out, that is alpha into inner product of xy is equal to inner product of alpha xy. So condition 4 is also true for all real number alpha. Now we prove if alpha is complex number. So first we shall show that inner product of I xy equal to I into inner product of xy. So replacing x by ix in equation 2, we get 4 into inner product of ixy equal to this one. So this can be written as by common I. So I into inner product of x minus iy, here common I, so this can be written as I into x plus iy, and I common, here also I common. So we can write this expression. So again applying the property norm alpha x equal to mod alpha norm x. Okay, mod I square, this one, into norm x minus iy square, here minus mod I square norm x plus iy square plus I into mod I square into norm x plus y square minus I into mod I square into norm x minus y square. Okay. Also we know that square of the mod I, that is 1. So we have this expression. Okay. Now taking I common. So we have this term first, norm of x plus y square minus norm x minus y square, this one minus 1 upon I x plus iy square, this is plus 1 upon I x minus iy square. Okay. So multiplying in these two terms in numerator and denominator by I. So we have this expression I into this, that is polarization identity. So 4 into inner product of ixy equal to I into 4 inner product of xy. So 4 cancelled out. This implies that inner product of ixy equal to I into inner product of xy. Now taking alpha is equal to alpha 1 plus I alpha 2, where alpha 1 and alpha 2 are real numbers. We have inner product of alpha xy equal to inner product of alpha 1 plus I alpha 2 xy. Okay. So using the third property of inner product, okay, that is x plus y z equal to inner product of xz plus inner product of yz. So this can be written inner product of alpha 1 x plus I alpha 2 x y. So applying this property, this is equal to inner product of alpha 1 x y plus I inner product of alpha 2 x y. Okay. So again using the property alpha x y equal to alpha x y. Okay, for any scalar. So here alpha 1 alpha 2 are real. Okay. So for real we can write the outside. So alpha 1 inner product of xy plus I alpha 2 inner product of xy. Can write this. So here common inner product of xy, that is we have alpha 1 plus I alpha 2 into inner product of xy. Okay. Here one mistake, this one is should be here inside. Okay. So using this property we can write I alpha 2 x I outside. Okay. alpha 1 plus I alpha 2 is alpha. So this can be written as alpha into inner product of xy. Hence equation 4 is true for all complex number alpha also. So thus we have proved that inner product of alpha xy equal to alpha into inner product of xy for each scalar. Okay. So here B is Banach space. B obeys the polarization identity and parallelogram law and satisfies the all condition of inner product. So B is a complete inner product space, that is a Hilbert space. In this lecture, we have discussed if B is Banach space whose norm obeys the parallelogram law and inner product obeys the polarization identity respectively, then B is a Hilbert space. These are the references which have been used in this lecture. Function analysis, Dover publication, written by George Beckman and Lawrence Naresi. Second, introductory function analysis with application, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rudin. Thank you.